Hello everyone and welcome to my symposium presentation. My name is Grace Goff and I'm a senior in the MSTC program at Paul Laurence Dunbar High School. Alongside my mentor, Dr. Sean Chang of the University of Kentucky Department of Computer Science, I was able to work on this project entitled A Computer Vision-Based Approach to Structural Health Monitoring. So to begin, I'd like to start with an overview of this presentation. We'll start off with introduction and background information necessary to understand the experiment. Then we'll get into the engineering goal and the methodology that I used to achieve that goal. Then we'll get into the data collected, as well as a discussion of the applications of that data, as well as its implications to this project. Then we'll end with further research that can be conducted into this topic, as well as my acknowledgements and references. So to begin, let's get into an introduction. So first off, what is structural health monitoring? It's exactly what it sounds like in that it's all methods used by engineers in order to monitor a building's structural health and integrity. This includes monitoring the motion of a structure. Monitoring the motion of structures helps engineers to both assess damage to a building as well as rebuild stronger buildings. This is especially important in areas at high risk for motion due to disasters like earthquakes or windstorms. However, current systems that are used to monitor the motion of a building are largely composed of hardware, like accelerometers, strain gauges, and sensors. These are, of course, expensive and labor-intensive to install, which means that building owners in areas that are at high risk for motion often don't have the necessary hardware installed into their building in order to correctly monitor the motion of a building. However, camera systems are readily available both in and around these buildings in the form of surveillance cameras, which leads us into the idea of using computer vision techniques in order to monitor the structural health of a building by monitoring its motion. This has begun being explored in certain previous literature, like a paper that used motion magnification techniques in order to monitor the motion of small-scale gears within an engine, as well as a paper that used vision techniques to monitor structural motion of a larger building. However, the algorithms discussed in that paper were non-optimized and therefore unable to run in real time. But that paper did inspire us to begin looking into a way to monitor the structural health of a building in real time, which leads us into the engineering goal, which is to create a program that is able to accurately track sparse pixel values on a structure in motion. Sparse pixel values is any sort of point on the frame that is in motion that is corresponding to one specific pixel value, as opposed to dense pixel values, which is all pixels within an image. So how are we going to do this? As an overview of the program, we'll begin by selecting a video for analysis. This is, of course, any video of a structure in motion. Then we'll get into selecting regions of interest within the frame. This is done by the user, and they are able to select any region within the frame that they deem to be of interest. Then, within those regions, corner detection is applied in order to select feature points, which are the points that we will be tracking, and then motion tracking algorithms, which we are using optical flow, are performed in order to actually track the sparse pixel values that were identified within the corner detection technique. So, in order to delve a little deeper to this, we'll start with the videos that were used within this project. So most of the videos that we analyzed were from an experiment that was a 5-story building on a shaker table. This was conducted at the University of California, San Diego, and was imitating an earthquake that occurred in 2012 in Alaska. So it's a fairly high-scale earthquake. So the motion is fairly large to the building. However, the building is very large scale in that it is 5 stories life size, so it's easy to monitor its motion. Additionally, cameras were placed all around the building so that we had several different angles of the shots. However, the camera was stationary since this was done in a lab setting, which would not occur in real-life settings, but made it much easier to track from a lab perspective. Additional videos were also analyzed. However, since these didn't have ground truth data, which is the actual data collected by those accelerometers, strain gauges, and sensors that I discussed at the beginning of this presentation, we weren't able to use those to compare, and all analysis of those were done qualitatively by me, in that I simply watched the points move around, and if they were jumping or moving in a way that they weren't supposed to, I knew that it wasn't working. And if they were mostly latched on to the point that they were trying to track, then I knew that I was accomplishing the goal. Most of those videos were done before we got into the bulk of the presentation, which was in the first videos that I selected. So when you pull up the program, the first thing that it asks you to do is to select an ROI. ROI stands for region of interest. This is a region that the user deems to contain a feature point, which is a point that you would want to track throughout the video. For example, on this image here, the user is selecting an ROI. The feature point in this region is probably this corner right here. Since all feature points need to be easily identifiable in each frame, they're usually deemed as corners, which leads us into the corner detection algorithm. So in computer vision, a corner is defined as an area of an image that has a high image gradient in multiple directions. Think of a black square on a white piece of paper. If you were to shift up the paper, you would notice the difference between the white of the paper and the black of the square, as well as if you were to shift sideways from the white of the paper to the black of the square. That difference in intensity from the black to the white is considered an image gradient. And since that is identified in multiple directions, up and down and side to side, that point would be considered a corner. So these are the best points to use as feature points because they're easily identifiable in multiple frames. So within those regions of interest, we use Shitamase corner detection, which is a specific algorithm that is able to identify corners that are rotated, and it's very optimized, so it's able to choose the best point in that ROI. This is done by selecting the number of points desired to be 1 and making the quality threshold very low so that at all times a corner is selected. This algorithm was already present in the library of functions that I used during the programming portion of this, which is called OpenCV. It's a library that is open source computer vision algorithms. So after the points have been identified in this step, we then need to get into actually tracking them. So to do this, I use a function called the Lucas-Conade optical flow algorithm for sparse pixel values. Within the OpenCV library, which is the library of functions that I used when programming this, it's called calc optical flow per LK, which stands for Lucas-Conade optical flow. So what is optical flow? That is the observed motion of objects in a scene, specifically their motion vector between frame A and frame B. So it's also reliant on assumptions that the displacement between subsequent frames is small and the pixel that we're tracking maintains a constant intensity value, which means that if you were to grayscale an image, from frame A to frame B, that pixel would have the same color value, which is its intensity in a grayscale image. So how do we find that motion vector, which is the optical flow? What it does is create an equation to describe the motion of the one pixel. If you were to consider the intensity of a pixel at point XY on a frame, and then consider the intensity of the same pixel at point XY on the second frame, the difference between those X's and those Y's would be the motion vector that we're looking for. So I was able to set up an equation that describes motion from point in frame A to frame B. However, there are several unknowns in that equation, so we can't solve that directly. So what it does is assume the same motion vector for surrounding pixels, which makes sense because in any sort of motion scenario, you usually don't have one pixel just jumping around by itself. This creates a matrix of linear equations, so you now have several more. For example, if you were to make a 3x3 grid around the point you're trying to track, you now have 9 separate equations that you can solve for this. These still have some unknowns, so what this does is use least squares regression and its knowledge of existing image gradients in order to estimate the motion in the scene. For example, this is a picture that somebody used this technique on to monitor the motion of a car, of several cars on a freeway. For example, this car would have started here, and as it drove down the freeway, you'll see that the point that is on its headlight here moved from this point on the freeway to here. And cars that started here have moved out of the frame, and over here, the car has moved into the frame. So you can see that this works in order to monitor a point's motion during a video. So as an example, I'd like to show you this function in practice. So if I skip up to anywhere in here really, you'll see this blue point and this green point. These are 2 points that are being tracked during this video. This is the basement view of the same building that I described at the beginning, in that it was conducted at the University of California, San Diego. So you'll see that these points are latched off to the point that they're trying to track and are not moving even when confronted with obstacles blocking their view, like this wire, and motion. As you can see, this one tracks. So qualitatively, this would prove that this is working well. And this is what I did during the portion of the experiment where I was simply watching the videos. So it's easy to see that this is doing what I wanted it to do. However, we now get into the actual data collected. So for example, this is the motion that was collected as part of the actual experiment at the University of California, San Diego. So this is the actual motion of the building. This here is the motion that we collected in our tracking algorithm. It's hard to see because these aren't laid on top of each other, but if you were to look at this, the differences in motion line up almost exactly. Of course, their amplitudes are different because their units are very different, but this is accounting for a sort of relative displacement, but their frequencies are very similar, which is a good sign that this is doing what we want it to do. It's easier to see on this graph here, where we compare the experimental data to the average of 0.7 and 12 that were collected on the tracking algorithm. As you can see with these laid on top of each other, you can see almost no blue because the red, which is the data collected by me, were almost identical. So since their frequencies are so in line, that helps to show that this is very accurate and has completed the engineering goal. So of course, the discrepancies in amplitude, some little bit of time has to go with a lot of unit conversion. The actual conversion from pixel distance to actual distance is very different. So of course, there's going to be some differences in that, especially if the scene is tilted in a way. Since that shifts the perspective, the pixel value will also change. This also shows that it's possible to use these optimized algorithms, which is the conjunction of the Shitamase corner detection algorithm with the Lucas-Conade optical flow algorithm, that are able to be used in order to monitor the structural health of a building, as well as showing that this is able to run in real time. In fact, when I ran this myself, it ran faster than the actual video played, which is a very good sign. And this could be a basis for future monitoring systems in high-risk areas. This, in conjunction with a little bit of traditional hardware, could be a better compromise in order for building owners to get the correct hardware installed in order to correctly monitor the motion of a building. And this could also be a cheaper, more widespread alternative. However, we need to get into some future research to make this actually usable in a real-life scenario. So of course, in any sort of disaster scenario, I would expect the camera to be moving as well. And that is not accounted for yet in this project. However, I've been looking into certain techniques that could be used to account for this. Also need to denoise image, which occurs to like a little bit of problems in the image itself. This would probably exist in surveillance camera footage, which is what we would be looking at primarily. Noise consists of any sort of corruption in the image. So if you see like on a black and white image, it looks a little bit staticky, that's sort of image noise. And so we would want to get rid of that in order to achieve the most accurate tracking techniques. It would also be good to do automatic identification of those regions of interest and feature points. This, we did make this available, but I took it off of the program in order to match up the points with the points in the sensor so that we could compare the ground truth data and the actual data. However, actually identifying those feature points automatically after they are being obscured by certain obstacles, like if in a windstorm it blew a piece of debris in front of a feature point, we would want the program to then latch onto that point afterwards. If these were implemented, this would be a really great way for building owners to maintain a cheap alternative way to monitor the structural health of their buildings in order to create the best buildings for our society and the safest society to live in. So I'd like to thank everyone involved in this project for allowing me the opportunity to work on it, especially my mentor, Dr. Sean Chang. I thank all of his work and support to me. I also thank Mrs. Karen Young and the MSTC program for allowing me to work with a professor at UK and allowing me time during the school day to work on this, as well as the Kentucky Young Researchers Program, which supports the research done at UK by students, as well as my family and friends, for all of their support to this project, for my family driving me there, and my friends helping me out when I got frustrated. This has really been one of the greatest experiences of my high school career, as well as my life in general, and I'm very glad that I got to experience it, so I'd like to thank all of the people involved. So to conclude, here are my references. And thank you so much for watching. Sadly, this is virtual, so I can't answer any questions, but if you do have any, I would love for you to email me at the email listed below. Thank you.